Right. So this is a very brief introduction to the finite element method and to the process that is involved when you use this method in industry. The idea, excuse me, the idea is that this method is gaining popularity, and it's been gaining popularity for the last decades, 2 or 3 decades, or even more. And the reason is very simple. It allows you to cut down the number of experiments that you need to do. Okay? It's as simple as that. Experiments means a lot of money, but more important for industry is actually the time, okay? Because time is the most expensive thing for them. And the idea is that you need to see the finite element method as a way to replicate experiments in a virtual environment, because this is what it is. Okay? And the process goes from a CAD model. Okay? This is a designer, someone that is in a department working with CAD software. The majority of you have seen CAD, either AutoCAD or CATIA or SolidWorks, whatever. They spend the time doing the design of a certain component, and then they pass this design to the department in charge of doing the finite element simulations. And the first thing these guys do, they generate a mesh, which is what you see in the center. Okay? A mesh for this particular component could be made of tetrahedral elements, like in the example. Okay? Just a subdivision of the geometry into smaller pieces, which are called finite elements, by the way. Okay? This part of the process, I'll talk a bit one day of the course about mesh generation. Okay? We are going to mainly focus on the second arrow, which is having a mesh. How do you do the finite element analysis? How do you compute the solution? It could be a stress analysis like is shown here. And at the end, what you get is a color picture by showing you the stresses, for example, or displacement. It could be a thermal problem, and you display temperature. It could be a flow problem, and you show velocity or pressure. Okay? It could be anything. So we are going to focus on how do you go from a subdivision of the space to the actual solution for different problems. And for the mesh generation, I will talk a bit, as I said, because people tend to think, especially people that use commercial software like ANSYS, tend to think that that's trivial. This part is really trivial because you import a CAD model into CATIA or into ANSYS or into Fluent, whatever, and you press the button, give me a mesh. And the software actually, in the majority of cases, will give you a mesh. Okay? But when you are working in industry, you actually need to take decisions that the software is not going to take for you, which is what type of mesh do you want? Is a mesh like this one on the right, made of hexahedral elements, like little cubes? Or is a mesh of tetrahedral elements, like this one? Is a mesh with really large elements, almost uniform? Or is a mesh with localized refinement? And in order to understand what is the choice that is suitable for me, you need to actually feel the process. And when I refer to feel the process, I refer to the actual physics. If you are an engineer, a civil engineer, you are supposed to know about the stress analysis, right? And you are supposed to know that this mesh, or this one in here, the ones on the right, are really bad for a stress analysis. Why? Sorry? They are very coarse, but why particularly stress analysis they are not good for? Yeah. You know, as an engineer, that stress is going to be localized near the corners. So that makes sense to do this kind of meshes, where the elements are big in certain areas, but they are big in the areas where the stress is going to be pretty uniform. And the mesh is refined in regions where you are supposed to have stresses, right? Aerospace. Who is aerospace in here? Probably the faces that I don't know. But a particular problem for you, similar to that one, would be flow around wings. You know that near the wing, you got something very particular that is called, in the normal direction, the velocity changes very quickly. How is that called?
Flow separation.
before that, before it separates. Boundary layer. The boundary layer is a region where you have a really high variation of velocities. You will need to refine in that region, not in the far field, where the velocity is pretty much uniform. So that's your knowledge. It depends on your background that you will need to do that. You will need to make choices. Okay? And with the coursework, what I will try to do is just to train you in that respect. Okay? You try different types of meshes, different levels of mesh refinement, and you will need to comment on the results in your report. Okay? But as I said, mainly we are going to look at this part in the course, in this module. And just a few pictures now, just to show you applications. I think it's always good to have a look at different applications. And I'm trying to find or to show you something slightly different to what you're used. I think that here having this split in civil and aero, it's very typical that the civils think that this is mainly used for structures when you design them, okay, before you design them. And for the aeros, well, external flows I think is the main thing that you might be thinking on. So just to try to show you something different, this is the use of finite element that was done when dismantling a bridge. Okay? Obviously, they used finite elements before to design it, but then at some point they wanted to dismantle this bridge. And the problem was, okay, in what steps do we do this? Okay? And you can see, there's a bit of an animation, that they were doing a stress analysis of this structure at every step of the dismantling process, just to make sure that this thing was not going to collapse. So it's something, you know, slightly different to what you're used. This one I also like it because it's, again, out of the standard use of finite elements. This is in a school here in the UK, and it was the analysis of the flow vibrations. Okay? So the objective here was to compute not displacement, not stresses, not flow velocities, but actually the resonant frequencies of a structure, okay? Because this is going to be something important in case of, for example, an earthquake, something like that. Okay? And the last one is aerodynamics, is the design of large passenger vehicles. And here, what I like about this simulation, or the reason why I selected this one, is because it's not only about external aerodynamics, which is quite important in these vehicles. Okay, you want to reduce drag, obviously, because that's going to affect fuel consumption and emissions. But also, we are at a point in time that the computational resources are so high, we have supercomputers really, really fast, that perhaps in the past, that was the only thing that was studied. But now they study together the external flow and the internal one. So you have here some ventilation, right? And you can see the inside of this vehicle. Everything is meshed, not just the outside to analyze the flow around the vehicle, also the inside to analyze the flow inside the vehicle, because this is going to affect passenger comfort, for example. And we're talking about simulations with easily 200, 300 million elements, okay? That's the kind of things that these days they do on a daily basis in industry. Just a few examples, okay? And now, after all of this, we go back to the very basics, to the 1D problems in finite elements, okay? Today is mainly going to be just trying to refresh your mind with respect to the level 3 course, okay? So I'm going to introduce the essential concepts on the finite element method in 1D, and at the end you should be able to use this method in order to solve ordinary and partial differential equations. So I will present this layout. I'm going to follow it almost every time that we introduce a new problem. I will present the problem first. I will do what is called the weak formulation. Then I'm going to present the finite element discretization with the Galerkin method, and what is called the shape functions, with the objective to arrive to the famous system of equations. Okay? But I'm going to do it from scratch for this particular problem. So that's my equation, and I hope, I'm not going to ask the question, but everybody should be familiar with this one, otherwise I would run and cry and scream, is the equilibrium of forces, okay, in a one-dimensional elastic bar. So you have internal forces here. F is the external forces, and what you have, you add them equals to 0. That means that you have equilibrium. We are considering a bar of length capital L, okay? And then together with the equilibrium equation, we always need two things here. First, the constitutive relation, which is the relation in between stress and strain. And because we are starting the module, we are going to restrict ourselves to the simplest possible material, which is linear elastic. So the E is what? It's not necessarily constant, could depend on X, but how it's called? Yes, thank you. Young modulus, okay? That's a Young modulus. And epsilon, which is, maybe it's too trivial and you don't want to answer because this guy, it's a strain, okay? Which is written, this is the kinematic equation, is written as the derivative of the displacement. That's pretty standard, okay? So that's going to be our starting point. And I'm going to try this. Right. Can everybody see the slides on the center? Yeah, perfect. Because then I'm going to be writing here also. So that's our equilibrium equation. And if I introduce the expression of the stress is Young modulus multiplied by strain. This is the actual equation of equilibrium, okay? Here what you have is epsilon, and here what you have is stress, right? Agree? Right. So what we have is a differential equation where we need extra information. If we have second order derivatives, which is what we have, okay, because we have one derivative here and another derivative here, how many conditions do we need in order to be able to solve the problem? 2, okay? And these are boundary conditions, okay? It's information that we need at the ends of my bar, of my one-dimensional bar. There are two different types of boundary conditions. We call Dirichlet when we refer to an imposed displacement. So here, for this example, I am assuming that I know the displacement at the left end of my bar, at 0. Okay? I know my displacement is given to me, is data. And just put 2, just to put a number. Okay? Just to do an example with a number that is not 0. Because as you probably know, it's quite common when you know the displacement in one end is because it's fixed, like a beam, right? But I wanted to put a number that is not 0 so that you can see the implications, right? So first type of boundary condition is I know my displacement. The other type is I know the stress. I don't know the displacement, I know the stress, right? And in this case, I'm going to assume that I know the displacement on the left, I know the stress on the right. And I'm just putting another number, 3, just to see how we handle this data. Make sense? Right. I can have Dirichlet at both ends. Okay? I can impose the displacement at both ends. Agree? Can I impose traction at both ends? That's the first question. I'll leave it there. Okay? Because I think you need more than 5 seconds to answer it. Maybe more than 1 minute or 2. You actually need to sit down and write a bit. I'll answer it, but not today. So you have time to think. Right? Anyway, partial differential equation plus boundary conditions which for this example I'm saying one is Dirichlet, so imposed displacement, the other one is Neumann, so imposed stress. Okay? Right. Solving these problems is not easy. Solving problems like this one here. Problems where you have derivatives. And when I say it's not easy, it's not always possible to solve it with a piece of paper and a pen. Okay? And in the majority of cases, it's actually impossible to solve them analytically, exactly, by hand. It's not possible. Right? We don't have the maths necessary for doing that. It's not that you don't have them because you are studying an MSc. No, they don't exist. Right? So we cannot solve these problems. And for that reason, we're saying, okay, we're not going to try to solve something slightly simpler. Okay, we are going to try to simplify. We are going to try to find approximations for it. And the first thing we do, let me skip this one. I'm going to go back in a sec. I'm going to solve this problem instead. Okay? Which is an integral of all of this. Okay? So all this derivative here, a, e, du dx, plus f. Let's do this first, from 0 to L, and differential of x equals to 0. Okay? What is the difference in between solving the first problem I had and solving this one in here? Why am I saying that it's simpler, the one below? Because you might think, it's not simpler, man. You put an extra integral there to make things more complex. But no, I'm saying that it's simpler. Why?
Remove the dependency from x.
Sorry?
Remove the dependency from x.
Removed the dependency from x. Do we? We are integrating respect to x. The extremes. I'm not following you, sorry.
Just saying we're just taking the extreme cases.
What do you mean by that? Extreme cases. Extreme, do you mean the ends, 0 and L, or is that what you mean? Or, yeah? Not really.
You can discretize the data and you actually give them sort of numbers if you integrate an area. So you're taking a function, you're actually putting up numbers to it.
Yeah, I mean, let's think that this guy here is a function, isn't it? The displacement depends on the position, correct? So it's a function of x. That means that when I do this equilibrium here, what I have is a function. And I would like, my objective is to find the displacement that when you plug it into the top, you got residual equals to 0. R comes from residual. Okay? I use the letter R to refer to residual. So your objective initially is to find a function u of x. So the displacement at any point on your bar that makes this residual 0, exactly. That means that you can find a displacement that gives you equilibrium at all the infinite points of the bar. I'm saying the same in many different ways. Okay? But that's the objective of the first problem. By putting an integral, I'm saying, wow, the one on the top is too difficult. To have equilibrium at every single point of the bar is very difficult. But if I put the integral, I'm asking for something different. I'm asking for equilibrium on average. That's where the integral is coming from. Okay? So I can have a residual. In one place, I don't have exact equilibrium. Okay? The internal forces are slightly higher. But in another point, the internal forces are slightly lower. And on average, I got a 0. With this formulation, with the second one, I am happy with this one here. This is why I'm saying it's simpler, the problem. Right? Okay, but then, in a picture, if you like, what I'm saying is that I am happy to satisfy the residual zero on average. So let's try to do something better, like this. Are you happy with this kind of residual? The residual must be zero, okay? Because residual zero means equilibrium of forces. Are you happy with something like that? It satisfies that the integral is zero, correct? Because this area could cancel this one in here. But if I go to this particular point, my residual is really big, meaning that I'm not satisfying equilibrium very well at that point. So that solution looks a bit not very good. And this is why we are going to introduce our test function. This is what you have here on the slides. Okay? And then we're going to see how this test function is going to help us to avoid having these kind of bad solutions, like the ones I plotted here. Okay? This is what is going to avoid having this deviation. Right, so what do we have here? We are going to rearrange things a bit. Okay? We need to work out a bit this equation now. And in order to do that, what I'm going to use is the previous slide, which is an integration by parts, an integration by parts formula. The integration by parts formula is quite simple, but I'm going through it. What I have here is the derivative of a product, right? And I know that the derivative of a product is derivative of the first multiplied by the second plus the first multiplied by the derivative of the second. Everybody knows that. Right? Then, what we are going to do is integrate on left and integrate on the right. Right? We are taking the integral of this guy and the integral of these two guys, which is what is written next. So what I have is the integral of this derivative, fg, from a to b, or from xa to xb. The limits are really any numbers you can imagine, okay? And perfect. Now, this one in here, the one on the left, what you have is the integral of a derivative, right? So this is simply the function inside evaluated at the ends. The integral and the derivative, they are like opposite operations. And this is nothing but f g, how do I write this in here? Like evaluated at b minus fg evaluated at a. Okay? And now I'm going to rearrange. I'm going to put the green to one side and the rest to the other side. So you have df dx g, and then the rest I'm going to put it to the other side. So I got fg evaluated at ab minus the integral f derivative of g. Agree? So basically I took this one and I move it to the other side to allow me to isolate the green one. Yeah? That's the formula on the bottom here on the slides, okay? That's how you get it. So you simply take the derivative of a product, integrate, and rearrange stuff. Happy? Right. And now we are going to apply this formula here. Okay? So remember where we are coming from. We had equilibrium of forces. Now we wrote this equilibrium of forces in integral form. add this test function that so far is not 100% clear why it's there, but it's going to be in a sec. But now what we have is the following. We got, I keep going in here with my weak form. I have the integral from 0 to L, derivative of area stress multiplied by phi plus the integral of F multiplied by phi. Okay, that's my integral equation. I just split the equation into two. The one on the top. And I'm looking at this guy here, and I say, that looks very, very similar to what we've done in here, because we have something differentiated multiplied by something without the differential. The here. Okay? So I can apply the integration by parts formula on the top. Yeah? And what do I get? I got the integral. Let me write it in the same order. A sigma and phi from 0 to L minus the integral of A sigma derivative of the phi. Okay. This is this part here, doing the integration by parts formula on the top. So I have this part here, and I got the other part here. Okay, and the last term is really not changing at all. It's the force, the external force, multiplied by that. So far, good? Yeah? Okay. What have I done here? I got that's okay. Now I'm going to rearrange, okay? We are done. Just going to put the things in the right order, because I'm going to put this one first. Integral from 0 to L of A sigma is the stress, so that's Young modulus multiplied by strain, which is the derivative of the displacement. Okay, and then I'm going to say that this is equals to the part containing the external force plus the part on the boundary. Okay, just put to the left. Let's use some colors in here. This one is the one here, and this one is obviously this one in here, and then this one is here. Okay, just rearrange them. Which should be very, very similar to what we are getting at. Doubts, questions, anything? Nothing? If it's nothing, I assume it's everybody's following. Yeah? And the only thing that is written here is this term. You can write it as whatever quantity you have evaluated on the right minus the same quantity evaluated on the left. Okay? And practically done here. what I want you here, more than every specific step, which is something that you can obviously sit down and revisit as many times as you need, is the reasoning, okay? The why we are doing all of this, which is we have an equation on the top that is the equilibrium of forces. We are after a displacement that when we plug it into this expression, so you give me a displacement, I compute the internal forces with this displacement, and they are in equilibrium with the external forces at every single point. That was my original objective. And I thought, this is too difficult, sometimes impossible. I'm going to do it on average. Okay? And this is why we introduced the integral form. The integral form, we introduced it to make the problem slightly simpler. And then after that, it's all a bit of a game here, what we've done after that, because I use this integration by parts formula. And the next thing I want you to really understand, and let's see if someone can answer the question now, is why do we do the integration by parts? One thing is to do it, okay? But the other thing is that you understand why we do all of this. Otherwise, it looks artificial. It looks a bit nonsense if you don't get it why. Ideas? Maybe you don't know the answer, but...
We are decreasing the order of the derivative.
We are decreasing the order of the derivative. I'll give you that. What he means is, correct me if I'm wrong, is the original equation had second derivatives. Okay? You had dx outside and dx inside. Dx outside here, dx inside. So you had a second derivative of a displacement. And after all these little steps, we end up with first order derivative of the displacement only. I'll give you that, but why is this good? More reasons. It's a reason. It's one of the reasons, okay? But there are more. And I think that there is another reason that for an engineer, or given the problem that we had on top, should be more natural rather than these derivatives. What other thing do we have here that we didn't have in the original equation? Go ahead.
Able to sub in boundary conditions.
Exactly. All of a sudden, and that's the whole point of doing the integration by parts, this is how you never forget it. Okay? You do it, look at this formula. This is the integration by parts that you learn in school. Okay? What you're doing is transforming an integral in your domain to another integral in the domain. I want nothing here, but I have a boundary term. And if you remember the original problem, we have this data, and we need this data to solve the problem. So we need to somehow make use of this data, right? The boundary conditions. The information we know on the boundaries, the only way to make use of it is integrate by parts, because then you will have a boundary term and you can plug in the information you know. Right? Okay, so that's what you do here. And just to finalize with the equation here, what I would say is, look, on the right, I have a known value of the stress, if you remember originally. Okay, I knew the stress on the right of my bar, and on the left I'm going to say, look, I don't know this stress. What I know is the displacement. Okay? So what I'm going to say is choice, and this is a pure choice. Okay? I'm going to choose my phi to be 0 here. So I'm going to remove this guy here and say, because I don't know the stress on the right, let me handle the known displacement later on. Because here, there is not, in this equation here, it's not trivial, in this one, how do I use the information of known displacement? Because I don't have the displacement appearing here. Okay? So I'll handle it later. But remember, I haven't used it. Okay? Are we going to die here? Right, so 10-minute break, and we go back.